Hi everyone, welcome back to MATA02, the magic of numbers. It is bright and early on Wednesday morning. Today we're going to be covering a couple of different topics. The first one is we're going to be covering a little bit of material from List's book, How to Solve It. I'll put a link on the Quercus and the you don't really need this book. I'm just using it as a sort of template to guide the first part of today's lecture. And the second part will really dive deep in divisibility, so we'll finally properly get started in this textbook. Other random notes. I now have, in addition to the confusometer that we've had for a while this class, I also implemented an exclamometer. So if you really want to exclaim something, if you put exclamation points in a chat message, then it'll automatically show up on the exclamometer, just like the question marks do for the confusometer. Unfortunately, getting emojis working was a little bit harder. Like, I know how I would do it, but I would have to do it separately for each emoji, so I just decided on exclamations and question marks, since those are pretty standard and most people have those on their keyboards. So yeah, so more options for chat participation, and with that, let's go ahead and get started on today's lecture. How to solve it. So now, for that, I'm going to start by talking about some codified solution strategies that George Polya, he's a mathematician from the mid-20th century, came up with to on how to solve problems using a sort of mathematical mindset. So this isn't how to solve a particular type of math problem. This is just how do you solve problems in general if you want to think like a mathematician or someone a bit more quantitative. And there are several different steps to these, and you might have heard of some of these, since these are often how we teach problem solving to students. So, this is from a 1945 book. The first part is you really have to understand the problem. What's the start and end point of the problem? Can you rephrase the problem? Can you draw a picture to help yourself understand it? Second, you need to then devise a plan. So, what methods have you learned in class? Are there special cases that are easier? Can you work backwards? And one of the things that I think math classes spend a bit too much time on, though obviously it is important, is often in math classes we make you practice how to carry out the plan a lot. So this is often what you practice, but you have to be a bit careful. And one of the things is, if I, for example, tell you to solve a problem using a method, then I've already sort of skipped the first two steps, and I've made you just like jump straight to carrying out the plan. And this is super helpful because there are lots of things you do need to practice in mathematics, but in some sense that's less useful for solving general problems in your life. Because if someone's already told you how to solve it, then it's obviously you're skipping a couple steps there. And lastly, you should also look back on your work. Did you check your work with an alternative strategy? Did you sit back and reflect on what strategies worked for you on a particular problem, and can you use it for similar future problems? And so this is the sort of four-step procedure is a sort of really high-level general overview of how mathematicians think about problems. And I'm going to give some examples about how you can apply this to different levels of problems, ranging from the specific problems I have on the ungraded problems to all the way to the big picture problems of how do you invent numbers. And really just trying to show this is a general method that you can apply when you're trying to solve problems. So the first part of this is understanding the problem. So this is one of the problems from your ungraded homework. I heard that a lot of people had a lot more trouble with this problem in tutorial. So I was talking to your TAs, and they said that this problem was quite hard. So let's go over it again using this sort of four-part procedure. So first, what's the start point of this problem? To do this, you need to first identify what kind of problem you're looking at. What's the sort of point of the problem? What's your goal? Or, I mean, well, not quite what's your goal, but where does the problem start? What are you given? So what is this? Is it an equation with two variables, an equation with fractions? Are you given facts about the current state of the world? Or are you given a set of known operations? Okay, yeah, so this is... most people are answering B, and that's the most obvious thing. So, like, of course, you are given a set of known operations, so that is also another one of the starting points, but the sort of immediate starting point here is an equation with fractions. I noticed one person answered A. There aren't actually two variables here. There's only one variable, x. So we are looking at lists. So so fractions are the biggest part of this problem, and so it's useful to identify that as the sort of crux of the problem. Okay, so now once you've identified the start point, it's also important to identify the end point. Oh, so what's the end point? So is it knowing the value of x? Is it an interpretation of the equation? Is it a prediction for the future? Is it a newly invented kind of number? Or none of the above? Okay, so now you guys have already seen this, and you guys have seen this in tutorials, so you know the answer. The answer is that this is really just, this is pretty straightforward. Solve for x. We want to know what x is. So we want to know the value for x. Want to know the value of x. And another way of saying that is you want to know what does x equal. And so knowing that start and end point really then leads you to how do you devise a plan? So how do you devise a plan? Well, what are methods that you learned from manipulating equations? So why don't you just throw in chat some of these various methods that you've learned from manipulating equations, either in this class or in other classes. So for the record, that is a request for chat participation. So just like, what are all the different things? Like if we were in class, I would like then pause right now and ask you guys to like shout answers at me, and then I'd write them on the board. Okay, so we have one which is opposite operations. So another is you have to isolate variables, the distributive property, bring x to the same side, moving one of the x's over to the other side, rearranging, multiply by 35 on both sides, collecting like terms. Yeah, okay, so you guys have now given a bunch of the various methods that are we use. And so some of these include things like replacing a value with something equal to that value. So an easy example, if you had some equation x plus 2 is equal to 4 over 2, that is the same as saying x plus 2 is equal to 2 because 4 over 2 is equal to 2. So you can replace something with something that's equal value. You have your additive and multiplicative identities. So something like, let me use a different color. So like x plus x over 2 plus 3 halves is equal to 0. Well, you can replace that by saying something like, you can replace that with something like 2 over 2 times x. So you could do that kind of replacement, and that would also be the same thing. Or you can do the same thing to both sides. So instead of replacing with 2 over 2, another thing you could do is you could multiply by 2 for everything. So if you multiply by 2 for everything, you'd instead get something like 2x plus 3 is equal to 0. You multiply by 2 on both sides. We also have all our various properties. So commutative, associative, distributive. I think the E went on the wrong side there, but distributive property, etc. So that looks something like 2 times x plus 1. Well, we know that's equal to 4x plus 2 by using the distributive property. And if you go backwards, that's just factoring. And lastly, and this is quite important, and this isn't entirely a separate method, but it is useful to think about this as a separate method because we also have how to add fractions. So 1/3 x plus 1/2 x is equal to 2/6x plus 3/6x, which is equal to 5/6x. Okay, so we have a bunch of different manipulations, and then once you remind yourself of what these manipulations are, and in some of the problems we'll be seeing later today, well, later in this lecture, we'll be using other types of properties. So in this set, we used our addition and multiplication properties, but of course, we also recently just learned about exponentiation properties, and so we'll also need to use those eventually. So, well, how do we execute this plan? So that was only a sort of high-level plan. Use these manipulations to convert to x is equal to. And there are a bunch of steps that you can do. And I think I saw somewhere in chat, someone suggested that you start by multiplying by 35. Often it's easier to start by multiplying by the biggest number. If you multiply by the smallest numbers, you will still eventually get there. But let's start by doing that way. So let's multiply everything by 35. By 35. And so what do we get? Well, that's 30. By everything, we mean both sides. Do the same thing to both sides. 35 times 3. I'm going to write out a number of the steps. 3/7 x plus 2 over 35 is equal to 35 times 5 over 3x minus 14 over 15. Okay, so easy enough, right? Well, let's multiply it through. So let's see, what do we get? This should be 15x plus 2 is equal to 165 over 3x minus, let's see, this is 7 times 5 times 14 over 3 times 5. The 5's cancel out, and so you get 15x plus 2 is equal to 165 over 3x minus 98 over 3. Then, of course, well, what next? Multiply everything by 3. So multiply everything by 3. And you end up with 45x plus 6 is equal to 165x minus 98. So then if you subtract both sides by 45x. So note that someone mentioned earlier, move things from one side to the other. So that's not actually one of the basic operations. Instead, what you're basically doing is you're subtracting both sides by that item. So when you move 45x to the other side, it turns negative. That's a way of saying that you subtract 45x from both sides, and you get 6 is equal, oh, let me change my color back. So then you get 6 is equal to 120x minus 98. And, well, let's add 98 to both sides. And you get 104 is equal to 120x. And so when x is equal to 104 divided by 120, x is equal to 52 over 60 is equal to 26 over 30 is equal to 13 over 15. Is that 7.5 or 75? 7 times 5. So we have one solution here. Okay, so we have a solution. Are we done? I should have put a box here. Are we done? No. That is correct. We are not done. So yes, we may have gotten a solution, but remember we have 4 different steps here. So after we execute, we still have to look back on our answer and check it and see if we got it right. So let's look back. Did you check your work using an alternate strategy? So, when we're trying to recheck our work with an alternate strategy, one way of doing it for solving an equation is just to plug the number back in. So we have x is equal to 13 over 15. Well, let's plug that back in and see what happens. So we plug in our potential solution. Plug in potential solution. And so, let's see, what's that? That's 3/7 times x, where we plug in 13 over 15 for that, times 13 over 15, plus 2 over 35 is equal to 5/3 times 13 over 15 minus 14 over 15. Well, we can simplify a bit, because you'll note that this 3 and the 15 cancel out. That gives a 5. This 5 and the 15 cancel out and gives a 3. And what are we left with? We're left with 13 over 35 plus 2 over 35 is equal to 13 over 9 minus 14 over 15, which is 15 over 35 is equal to 13 over 9 minus 14 over 15. 3 over 7 is equal to 13 over 9 minus 14 over 15. And, well, things look like they might be going wrong. So if we multiply both sides by, let's say we multiply both sides by 15, so 45 over 7 is equal to, did I do that right? Yes, by 15. So then you get 65 over 3 minus 14 So let's 6 and 3/7 is equal to 21 and 2/3 minus 14. And so we end up concluding 6 and 3/7 is equal to 7 and 2/3. This is a problem. So we solved for, excuse me. Sorry, so we solved for x, but then when we went back and checked, things went wrong. So why did we not get the right solution? Actually, let me reset before you reply to this. Why did we not get the right solution? Well, was the answer that we did? Did we use the wrong strategy? Did we have an error in the execution? Bad assumptions? Or none of the above? Okay, yeah, so we have a mix of different answers here. Some people seem to think we had the wrong strategy, while other people think we had an error in execution. And so, in general, you don't always know why things went wrong. But if it's a type of strategy that you've used many times before, and you still got the wrong answer, then often you can then, your first guess should be that's an error in execution, and not that that was necessarily the wrong strategy. Because, like, I've solved a lot of linear equations before, and usually it works out. It doesn't work out this time, so that means that it probably wasn't that I had the wrong strategy, it's probably that I had an error in the execution. So, what went wrong? Let's see. So, let's work through everything again one more time, starting from the beginning. So, well, what did we do? Multiply by 35. Let me rewrite that. Sorry, I didn't rewrite the equation. 35 times 3 over 7x plus 2 over 35 equal to 35 times 5 over 3x minus 14 over 15. And what did we get? We had 15x plus 2 is equal to 165 over 3x minus 7 times 5 times 14 over 3 times 5. And we canceled those out. Well, wait a moment. Does anyone spot the error? So the error happened in this line. Something went wrong. No, not quite to 5. Look at all the things I multiplied. Uh, 14. Yep. We have a correct solution in there. It's not 165, it's 175. And this is what you get for trying to do mental, what sometimes happens for trying to do complicated mental math in your head. So, 35 times 5, well, that's 25, 15. So that's actually, sorry, I should write it where I have a little bit more space. 35 times 5, that's 25, 15, 175. Where did we get the 7? Oh, yeah, so that's actually another one of the steps that I sort of skipped, which is that 35 is equal to 7 times 5. And so I replaced 35 with 7 times 5 there. Okay, but like I skipped multiple steps, and sometimes when you're not careful and you skip multiple steps, then things go wrong. And it's not always obvious where things go wrong, and so if you are not entirely comfortable skipping steps, you should be really careful about doing it because, well, sometimes when you do that, things go wrong. Well, now let's carry this through again with the correct values. So 15x plus 2 is equal to 175x over 3 minus 98 over 3. Multiply everything by 3, so you get 45x plus 6 is equal to 175x minus 98. Where did the 7 times 5 come from? 35 is equal to 7 times 5. So this thing here was just the 35 in the distributive property. Okay, but let's keep on going. So we have this value, and now we're subtracting both sides by 45x. So you end up with 6 is equal to 130x minus 98. Add 98 to both sides. 130, and I'm going to flip it. So 130x is equal to 104. So x is equal to 104 divided by 130, which is equal to, if we divide both top and bottom by 2, 52 over 65, which is equal to, if you divide top and bottom by 13, which is a little bit less obvious, what property was distributed to get 7 times 5? Well, we know that 7 times 5 is equal to 35, and therefore, whenever you see this 35 goes into both the 5 over 3 and the 14 over 15, right? And so you're putting 35 into both, and so you can replace the 35 with a 7 times 5. Let me do this again. So it turns out that when you do this, you'll find this is 13 times 4 and 13 times 5. Wouldn't you just multiply 14 over 15 by 35? Yes, that is exactly what I did. Except I took another shortcut, which is, let me finish this first, and then so this is equal to 4 over 5. So what was the shortcut I took? The shortcut I took is that I have, let me put this in a different color. 35 times 5 over 3x minus 14 over 15. Just using the distributive property, you get 35 times 5 over 3x minus 35 times 14 over 15. Right? So that's distributing it into the two pieces. But then the next thing I did is I wanted to factor these out. So what's 35 divided by 15? When you factor that out, that is 7 over 3. And that just made it a little bit easier because otherwise I'd have to have really big numbers. Yeah. Okay, so hopefully that was, so I wanted to walk through this a little bit more slowly just because I know you guys studied this in tutorial already, but this seemed like one of the problems that there's lots of places to get lost. In exams, the answer we put is not in the simplest form. Will you be penalized? That's a very good question. The answer to that question is you will be if I say you will be. And in general, you should assume that you should put something in a simplest form. So on the exam and quizzes, I will try to be explicit about it, but you should generally put it in as simple a form as possible. I will often, like that actually reminds me, I will put on your quizzes and exams, you must put it in the simplest form possible. It'll be a minor penalty, but it will be a penalty. Okay, so that's this question. Rather than fractions, what if we do decimals as the answer instead? That's a good question. That again depends on the problem. So sometimes I will actually explicitly ask for fractions. Sometimes I will allow for decimals. But I will specify on the quiz. So you should be prepared to do either. We haven't really learned about decimals yet in this class, right? And so we haven't really learned about decimals, so I'm not going to ask you too many decimal questions. And I am aware that decimals are often easier on calculators. But in some sense, the calculators are only meant to be a tool. They're not meant to help you solve the entire problem for the purposes of this class. So if you answered that one as a decimal, well, I might, in general, I would give you most of the credit, but I might take off some points if I explicitly say I want it as a fraction. Okay, but now we have this here, and let's recheck our work. So, well, let's recheck our work. Does this solve it? Well, all we do is we plug it back in. So 3/7 times 4/5 plus 2 over 35. Is that equal to 5 over 3 times 4 over 5 minus 14 over 15? Okay, so if we multiply those out, that's 12 over 35 plus 2 over 35 is equal to, I'm not going to cancel this out, the 20 over 15 minus 14 over 15. So then you get 14 over 35 is equal to 6 over 15. And that is actually true, because you note that this is 2 times 7, and this is 5 times 7 is equal to 2 times 3 over 5 times 3. And those cancel out, and you get 2 over 5 is equal to 2 over 5. So that checks out. Okay, Well, now we've partly looked back and reflected. Well, but that wasn't the only question. It's not just checking your answer. Let's actually look back and reflect. So what? Oh, oops, I forgot to animate the slide. So, well, that's all right. I will not ask you to respond in chat, so let me cancel it out. So, I was going to ask, what strategies worked on this problem? What can you use in the future? And the answer to that is there are several things we did to solve this equation. One was obviously multiplying both sides of the equation by a denominator to simplify the equation. Another way of doing it would have been to multiply by 1, but then rewrite 1 as m over m as a fraction, but that can be a little bit more complicated to keep track of. But you will have to do that on some other problems. Then after you get rid of the denominator, we moved everything with an x onto one side and moved everything else to the other side. So by moving, we of course mean subtracting by it on both sides. And then of course, importantly, we check the final answer by plugging it in, because that can help when you make a mistake, which happens to the best of us. In fact, I'm going to take that as an opportunity to point out that I made a mistake last time, which some people noticed when they started writing it out, but no one really called me out on it. So in the future, when I make mistakes like this, hopefully you guys are checking me and you'll call me out when I say something really silly. So I had this question about $10,000 in student debt. And I said that it was 10,000 times 1.1 to the 10th power is equal to 61,159. That is not actually true. But if you go back and use the multi-step process, the first part is you have to understand the problem. So this is predicting the future value based on the early growth rates. Second part is devise a strategy. Well, you can multiply the initial 1.1 value by 1.1 10 times. We executed the plan, and we can look back and check. And there are several different ways of looking back and checking. In this case, well, you know that 1.1 to the 10th power is equal to 1.1 to the 5th power squared. And when you type those numbers into the calculator, 1.61 squared, that's equal to 2.59. So clearly there was a problem in their calculation. So when you, let me go back. And so when you actually plug this into a calculator, what you end up getting is that this is 25,937. I did not mean for this to be an error. That's an error that just happened because I accidentally typed in 19 instead of 10 because the 0 is next to the 0. That 0 is next to the 9 on my keyboard when I was throwing this into a calculator. So you have to be really careful about just throwing stuff into a calculator because even I do it, and when that happens, I make mistakes. Yeah, so I just wanted to highlight that, and I didn't want you to think you'd be owing way more money than you would from student loans. Okay, but we can also use this kind of strategy to talk about other kinds of problems. So these are both like specific problems that we're talking about. These are both very specific problems, not the sort of general problem. Oh, can you explain how we check that problem one more time? Yes, I will. Thank you for asking. So let me actually pull. Okay, so what is our goal? Unfortunately, this problem, you can't really just plug something in the same way as you plug in a value of x for solving an equation, right? So one thing that you have to do is you still want to solve this work a slightly different way, because if you solve it just the same way again, you're likely to make the exact same mistake. But instead, another thing you can do is you can realize that 1.1 to the 10 is equal to 1.1 to the 5th power squared. And so let's just typing in something different into the calculator, which means that I'm unlikely to make the same typos, for example. So if I go to my Chrome capture, and let's just go to Google. 1.1. So I originally typed in 1.1 to the 19th. That was my mistake. So you have to be a little bit careful. I typed in 1.1 to the 19th when I should have typed in 1.1 to the 10. But now that isn't necessarily the most obvious thing to figure out because, well, I don't actually know what 1.1 to the 10 ought to be, not a priori. But instead, I use the fact that if you want to check, one way of doing it is to rewrite your equation in a slightly different way. So 1.1 to the 5 squared should also give you the same answer. So if you go here, so 1.1 to the 5 is 1.61. And when you square that, you get 2.59. And you'll notice that this is different from the 6 point something we had earlier. And so that's one way of knowing that something went wrong the other way you wrote it. So even when you're just using a calculator, if you write your problem slightly differently and type things in differently, then that can help you check to see if you did the problem correctly. Okay. But yeah, so we have this process, and importantly, checking your solution is part of the process, and also reflecting back and thinking about what you did that you can then carry on and move on to some other similar problem. So now let's do a sort of higher level problem, right? So we invented negative numbers. Well, this is obviously a very different kind of problem than solving an equation. It's sort of much bigger scale in some ways. But you can still apply the same sort of problem-solving procedure to this. So the first thing you have to do is you have to understand the problem. The problem for negative numbers was when you have only positive integers, sometimes subtracting things doesn't give you a number. So the problem is 3 minus 5 is not a positive number. And so we didn't know what to do, or people didn't know what to do. And so you had to devise a new strategy. And of course, there are a couple of different strategies you could have done, but the one we did was we decided, well, let's invent some new numbers and give them a name. We'll call them negative numbers, or negative integers. But that's not the only thing we had to do. So we had to do several other steps as well. We also had to create a new number system with both the positive and negative integers, and then see how they all fit together. This is why we created the number line with positives and negatives. And we figured out, using the rules of addition and subtraction, how they all fit together. So we need to check that the addition and subtraction both still work properly. And of course, so once we devise that strategy, you also need to execute the strategy, which is to actually do the math and see what the new addition and subtraction tables are. And then, well, we need to look back and reflect. Does this still solve the original problem? Well, yes, because now we have that 3 minus 5 is equal to minus 2. Can we use this kind of method on other problems in the future, like division and fractions? And the answer to that was also yes. We also saw how to do this. We invented fractions for the purpose of letting us do division on more things. And if you're ever going to invent a new number, well, you have to think about all of these different steps. Like, what kind of problem are you solving? What is the overall strategy of inventing new numbers? How do you execute the strategy, and how does that relate to all these other things that we've done? All these other inventions of numbers that we've done, or maybe other similar kinds of problems. Hopefully that sort of makes sense. I'm sort of trying to give you a high-level overview of how mathematicians think. Like, in some math classes, all you get is I give you a bunch of algorithms, I give you a bunch of methods, and you memorize them and do them. And yes, there is some of that in this class, but I really want to emphasize that these methods that you had to memorize in the past, that's all because someone came up with some idea and solved that problem in this sort of general way. Okay, so let's try it out. So let's say I want you to rewrite this particular equation as m over n, where m and n are both integers. And let's go ahead, since this was asked earlier, and let me add, and it is in simplified form. Okay, so what's the problem here? What are we trying to do? Well, m and n, where m and n are both integers. Well, then really what the problem is I just want to turn this thing into a fraction. And I want to turn it into a simplified fraction. Well, then you have to design a strategy. Well, what kind of operations does it look like we'll have to do for this kind of problem? Well, it looks like there are a lot of powers here, right? So you have to use the exponentiation rules. So I have the 5 of them listed here, and you have to know all these rules. So if you see this on a quiz, hint, hint, you will see this on a quiz, you'll need to know all these exponentiation rules and be able to apply these things to implement the strategy of using exponentiation rules to turn this into just a single fraction. And of course, at the end, you also need to look back and reflect. Can you check your answer? And sometimes it's easier than other times. Sometimes it's hard to check your answer. Sometimes there are other different ways of checking your answer. Like maybe if I ask you to do something as a fraction, you can still check it using a calculator in decimal and then seeing if the decimals match. So that doesn't allow you to get, so this way your calculator won't let you get the answer immediately, but it will allow you to check if you got the right answer. Let's try it out. So what is this thing equal to? Oh, let me reset the chat before you start typing stuff in. So we want to convert this thing into a fraction. So people are starting to reply. We have some A's, we have some D's. Okay, we have a lot of these. C, a couple A's. Okay, so let's work this through together and see what happens. Well, the first thing to notice is that 8 to the 1/4 power. What is 8 to the 1/4 power? Well, 8 to the 1/4 power is the same as saying 9 to the 1/2 to the 1/2. So let me just notice that 9 to the 1/2 to the 1/2 is just the square root. Oh, sorry, I wrote that wrong. That's 81 to the 1/2 to the 1/2. So let's 81 to the 1/2 to the 1/2 is equal to, well, that's equal to 9 to the 1/2. So the square root of 9, which is equal to 3. So this thing here is equal to 3. So this entire thing is equal to 3 cubed times 2 to the minus 3 times 2 to the 2. But 2 to the minus 3, when you multiply like powers together, that's the same as adding them together. So this is the minus 3 plus 2, right? Oh yeah, so you can just do the 4th root of 81 instead, but you have to know what the 4th root of 81 is. So what happens when you do this? Well, this is now equal to 27 times, well, 2 to the minus 1, and 2 to the minus 1 is just equal to 1 over 2, so it's equal to 27 over 2. Okay, so now this is an answer I just got by writing this stuff out. Now, let's check to see if this is right. So now, as I was saying, like, it's sort of hard to figure out how to check these things, but one thing you could do is if you happen to have access to a calculator, well, what happens if we plug these things into a calculator and see if they get the same number? So let's go back to Chrome. So I have a calculator here. Well, what are we trying to do? So let's say 81 to the 1/4 power. So luckily, when you're on a calculator, and this entire thing cubed times 2 to the minus 3 power times 2 squared. Well, what's that equal to? That's equal to 13.5. Okay. Well, is 13.5? What about 27 divided by 2? 27 divided by 2? That's also 13.5. And so that means that we did indeed get the right answer. And you'll notice that you couldn't actually have, if you just typed this into a calculator, you wouldn't have been able to solve it because I asked you for this in the fraction. And yes, in this case, you could have taken this decimal and turned it back into a fraction, but that won't always be the case. And so just because you can use a calculator doesn't necessarily, but you still can use this to double check your work. Okay, so let's go back over to the PowerPoint. Let's do a different one. So let me reset before you reply. So what about this value? Okay, yeah, so you guys all saw the trick. So you could actually go through and solve this all, but another thing to note is that any positive number to the 0th power, and you do have to be a little bit careful to make sure this isn't a 0, but you don't have to be that careful to make sure it's not 0. This is just equal to 1. Yep. Okay. So that's one kind of problem that you will be seeing, and on a quiz, I might tell you that you have to do it using the exponentiation rules and not just throw it into a calculator because, well, I'm trying to teach you how these numbers all work together. and I don't want you to just plug them into a calculator, which is why I might tell you to give it as a fraction rather than as just a single answer. And I might even tell you to show your work. In fact, that'll be pretty common. I'll ask you to show your work. So you're allowed to use a calculator, but you still have to show your work, which means that you can't just plug everything into a calculator. The calculator is there to help you check your work, but not necessarily to solve it for you. Now, normally, when I teach this, people often ask, well, why do I need to learn that when I always have a calculator sitting in my pocket? And the reason for that is because this is not a math class where I'm here to teach you things that are useful. Like I said at the very beginning of this class, this is a math appreciation class, sort of like an art appreciation class or an English appreciation class. We're not actually teaching you math because it's useful. We're teaching you math because it's cool, and we want you to learn a new way of thinking. So that's the answer to that question in case people had it. Okay, so now let's try it out again. So I have a different problem here. I want you to rewrite, oh, actually, I wrote this problem down wrong. I should have a -1 there. Okay. So let's rewrite this as a product or quotient of powers in which each variable occurs exactly once and all exponents are positive. And we're going to assume that all variables represent positive real numbers only. So now, this is slightly more complicated, right? But basically what we're saying is we want to write this as something like a fraction, but of course we have x's and y's and z's instead of actual numbers. But we want to write it as a sort of fraction in x, y, and z, where all the powers are positive. And you don't have x on both the top and bottom, so you cancel those out. So let's try to understand the problem. This is somewhat similar to previous problems, except that instead of wanting integers at the end, we want positive powers of x, y, and z. Well, what's the strategy? We can use the exponentiation rules to remove the negative powers and cancel out. And after we're done, we'll of course have to, oh, sorry, I didn't have, you also need to execute the strategy. Let's insert in there execution. And we also need to look back and reflect. So is there an easy way of checking this answer? How similar is this to solving the previous problem? And it turns out that this is quite similar, but it's still not quite the same thing. So, but I will have you guys do it regardless. So let's have you all try it out. And let me reset before going forward. So now, remember, you have to use all the 5 exponentiation rules, and I strongly recommend that you practice the exponentiation the problems enough that you have them memorized, because otherwise you'll be going back and referring to them over and over again. Okay, it looks like we're starting to get some answers in. Oh, it looks like almost everyone agrees on... Okay, so we have mostly D's, a couple C's and a couple A's, a couple B's. Okay, so we have a bunch of different answers. So let's actually... So it looks like D is the most common answer, but let's try plugging, let's try solving it and see what happens. And one nice thing about having... we'll get there in a moment, about one of the nice things about this sort of equational form. So what is this equal to? Well, let's try to solve the inside first. So what is z to the 0? Well, z to the 0 is just equal to 1. So this is x to the minus 1, y squared, over x cubed, y to the minus 1, z squared, to the minus 1 power. And this is because z to the 0 is equal to 1. Well, now I'm going to multiply by 1 on both top and bottom by multiplying by x over x times y squared, oh sorry, not y squared, y to the 4th over y to the 4th. And those are both equal to 1, so you can just multiply that and you get the same value, times x to the minus 1, y squared, x cubed, y to the minus 4, z squared, minus 1. So this is just multiply by 1, which is equal to something like x over x, which is equal to y to the 4th over y to the 4th. And once you multiply this out, what you end up getting is that this is y to the 6th over x to the 4th z squared inverse, which is equal to x to the 4th z squared over y to the 6th, because this is a reciprocal. Okay, so we got D, so that is the correct answer. But now, one of the things you might want to ask is, well, how do you check this? So in the previous example, I just had you use a calculator to check it, right? Because if I give you a calculator, then one of the things you can do is you can, well, you can just throw the numbers in. But now what about in this case? How would we check this? Does anyone have any idea about like an easy way to check this answer? So let me give you a hint. I said that work backwards. Okay, so working backwards does work. In this particular case, you can work backwards, and you can check to see if each of the different things does get you the right answer, but that takes still a significant amount of time. We could use a different method. So instead of doing this in this step, maybe my first, so that's actually one way of doing it differently, is maybe instead of doing that, maybe my first step is I'm going to flip everything. X cubed, y to the minus 4, z squared, over x to the minus 1, y squared, z to the 0, and then solve it like using a slightly different ordering. So yeah, that can work. But another thing you can do, oh, yep, Andrew has the answer there. So you can substitute values into the variables. Remember, we want this to be true for all x, y, and z that are positive. And so we can just pick numbers for ourselves and plug them in and hope that they work. So I'm going to plug in, let's say, x is equal to 1, y is equal to 2, and z is equal to 3. Okay, so you can pick other numbers. I'm going to pick these 3 numbers for no particular reason. Actually, let me make life, for no particular reason. So if I plug it into this bottom equation, if I plug it into the top equation, what you end up getting is you get 1 inverse is just 1, so that's 1 times 2 squared, 3 to the 0 is just 1, over 1 cubed times 2 to the minus 4 times 3 squared. So that's equal to 4 over 1 over 16 times 9, which is equal to, multiply the top and bottom by 16, 64 divided by 9. Okay, and if we plug it into the bottom equation, what you end up getting is 1 to the 4th times 3 squared. Oh, sorry, I'm using green. I said I wouldn't use green. I should just get rid of that color on my palette. So 1 to the 4th times z squared, so 3 squared, over 2 to the... Oh, wait, I did that wrong. I forgot that all of this was... I had to take the inverse. So that's actually equal to 9 over 64. Yeah, over y to the 6, so that's 2 to the 6. So that's equal to 9 over 64. And so these two are indeed the same. So for when you're working with something that's in x's and y's and z's, one thing you can do is you can just substitute values in and to check to see if you got the right answer. Okay, so with that, did that make sense to everyone? So just want to make sure before we move on that you guys have a good sense of all these different strategies for checking your work. Okay, great. So let's move on. Let's go back to thinking like a mathematician. So we have a lot of different numbers now. We have natural numbers, negative numbers, and fractions. Do we need even more kinds of numbers for powers? And let me reset before you answer. We have a couple people who are saying yes, a couple people who are saying maybe, and a decent number of people who are saying way too many numbers. Well, unfortunately, if you hang out with mathematicians, there will be lots and lots of numbers, lots of different kinds of numbers. Okay, but we have a mix of people who are saying yes, and a mix of people who are saying no. A couple people are saying no, a couple of maybes. Okay, well, let's think about this. Why would we need more kinds of numbers for powers? Powers are just repeated multiplication. And we already have all the numbers we need for multiplication, right? So like 2 to the 10, that's still going to be one of our numbers because that's just going to be 2 times 2 times 2, so on. So the answer to the list is actually no. We don't need more numbers for powers. What about for roots? Let me reset. What about for roots? Do we need more numbers for roots, though? Okay, so we have more people saying yes here. A couple people said no, a couple people said maybe. And one way to think about this, though, is if you think about it, when we did addition, we didn't need new numbers. It was only when we were going to reverse addition that we needed new numbers. For subtraction, that's how we got the negative numbers. When we do multiplication, we don't need new numbers because that's just repeated addition. But then when you reversed it by doing division, then all of a sudden you needed fractions. And the same sort of thing happens here. So when you do squares and like cubes, those are when you do powers, you don't need new numbers because it's just repeated multiplication. But somehow for the reverse operation of taking roots, you do need new numbers. So things like the square root of 2 is not a fraction, which we'll get to a little bit later. We'll actually prove this. When people first figured this out, people were really scandalized because they're like, wait a moment, can you not write everything as a fraction? I thought we were done inventing numbers. It turns out we're not. So we'll be inventing more numbers, things like the square root of 2, later in this class. But not yet. We're done inventing numbers for now, and we're going to spend a lot more time on divisibility, which will be the next part of this class. But for now, it is halfway through the class, so let's take a 10-minute break, be back at 10:01, sorry, not 10:01, that's a minute in the past, 10:12. So everyone come back at 10:12, and I'll see you in a little bit. It is break time.